something that already appeared in Safranov's talk, that are the shifted symplectic things. And the point of this talk basically is to give concrete and explicit formulas and examples basically of these objects. So let me make first a motivation, that is that there are like three worlds, and one is like physics, the other is geometry, and the other is algebra. And these three worlds basically encompass three different aspects of the theory that basically are the same. So the first one that appears is the physics one, and this was the Q manifolds. And these Q manifolds are basically graded manifolds, so you should think them as manifolds endowed with some extra fermionic coordinates and some differential that allows you to make like homological algebra on this kind of objects. And these Q manifolds, it is used or well known in physics, for example, to use of sigma models, this so-called topological quantum field theory is known as AQSIT. The other side that we have here is like differentiable stacks. And this is basically a framework, or stacks just, a framework that is usually used in algebra, or algebraic geometry. And as we already saw in the talk, what things are happening here is like Artin stacks and things like that. And there is something in the middle that is linking these two worlds that are the Lie groupoids that I want to explain.
Miguel, let me ask you, on the right side, of the algebra side, do you mean the higher differential?
Yeah, these are n stacks, and this should be degree n if I put things here. That's right. So how these three things are more or less related one to them. So I think that the first idea, passing from Q manifolds to Lie groupoids, was given by Severa, and the relation is like a Lie functor. So this should be differentiation, and this should be integration. And I think that on Wednesday there is the talk of Chen Chan, more or less talking about these objects here, what happens, how to pass from Lie groupoids to degree n Q manifolds and vice versa. So I will not explain too much about that. And here we already saw it, that the way of passing from Lie groupoids to differentiable stacks is by taking Morita class. And if you have a differentiable stack, you should think a Lie groupoid as an atlas of this object. And what happens here is that these objects have maybe this color. Here there is a notion of what a symplectic Q manifold is. There is a notion of what this shifted symplectic or M shifted symplectic differentiable n stack is, and what happens here in the middle. Well, the history is more complicated than this diagram, but it's illustrative. What happens is that this world and this world are not exactly the same, because the symplectic here is not, let's say, up to homotopy, whatever does it means. So in general, the symplectic degree and Q manifolds are more restrictive than the shifted symplectic ones. But whatever, this is the idea that you should have in mind, that here you can put the M shifted symplectic groupoids that I will talk today in the middle, and more or less this diagram is something that relates the three sides of the history. So on one side we have physics, geometry, and the other algebra. So the M-shifted symplectic Lie groupoids were, as far as I know, defined here like 8 years ago by Getzler. And in degree 1, so one shiftedly, one groupoids, I will explain that are the quasi-symplectic or pre-symplectic or twisted pre-symplectic groupoids, already defined here, but in higher degrees these objects are, well, not so well known, or there are not too many examples and many ideas to give some examples here. So before going into, so the main example that we have is to, well, I will put it here. There is an easy example in degree 2 of, so degree 2 symplectic Q manifolds are the same as current algebroids. So when n equal to, I have here current algebroids. And there is a well-known, or an easy well-known example of current algebroids that is a quadratic Lie algebra. On the other side, here, the differentiable one stack, that is like two-shifted symplectic corresponding to quadratic Lie algebras, is BG, with this omega BG that is also encoded by the pairing. So BG here is just the classifying stack corresponding to the Lie group integrating this Lie algebra. And I think that it was shown by Pantev, Bassiam, and Beshosi that this one stack carries a two-shifted symplectic structure. And the idea is what should you put here in the middle, and what we will construct is 3 Lie1 or Lie2 groupoids that fits here in the middle, and the point is that all them will be symplectic Morita equivalent. So all them codify this shifted symplectic stack, and at the same time, all them should differentiate to this quadratic Lie algebra. And just in one case, we are able to show it that that's the case, but yeah, anyway. So the main goal is to construct this. Let's construct Lie2 or Lie1 groupoids, and these are two-shifted symplectic. Okay, so before to make that, I want to, explain a bit what is going behind of all these things, and start by the beginning. So, first of all, what is a Lie groupoid? So, and in order to talk about Lie groupoids, I should talk about simplicial manifolds first. So what a simplicial manifold is? A simplicial manifold is just a functor from the category of finite ordinals to the category of manifold, and this category have as map ordinal preserving maps. So more concretely, that this abstract definition is that a simplicial manifold is just a collection of manifolds from I to 0 to infinity, and then these are manifolds. And here, when I say manifolds, I'm working in the work of probably infinite dimensional Banach manifolds. So those are manifolds for me. And then I have some phase maps that are maps going into this direction for k going from 0 into L. Sometimes people pull it a super index here indicating the L. I will just drop it. These are called phases. And then you have degeneracy that are sk going from xl to xl plus 1, and the k is into L. And they satisfy simplicial identities Well, I will write some of the simplicial identities to have an idea of how they look like. If I, or for example, this mixed one, di dsj, and this is equal to sj minus 1 di if the I is equal to j, identity if the I is equal to j or j plus 1, and sj di minus 1 if the I is greater than j plus 1, and there is also, well, I just put it, is j plus 1 si if the so those are the simplicial identities. So which is the idea behind these simplicial manifolds? Well, the idea is that we can think x0 as points, x1 as directed arrows. So I just think it this, and I have 0 and 1 here. x2 as triangles. 0, 1, 2, and my direction of the arrows goes like water, so from higher to down, and so on. So that's the idea. So this thing is like encoding like arrows. You are adding arrows to your manifolds. These are like the points of a manifold. These are like arrows. These are like triangles, and then you have tetrahedrons, and so on. So I'm replacing just manifolds by these simplicial manifolds in order to, you know, put in more things into my pictures. And then the simplicial identities is just telling you, you know, how this, all the simplices that are this, how the faces and the generacies, how to include and go up. And there are two important simplicial sets that we needed. One is the simplicial L simplex. Is just denoted by this, and these are maps from JK to L, and these are Fi less or equal than Fj, and the other is the horn. And the horn is just Lj horn on degree k, and these are just the elements of my simplicial L simplex on degree k. So the k is indicating how are these manifolds, because these are simplicial manifolds. I'm not telling you which are the faces and the generacies, but anyway, and these are just on degree k, I put it the elements j plus 1 and 12 that are not containing into F0. So basically, this horn thing, the only thing that is doing is just taking out the j face and the face of the top degree of my simplicial L simplex. So this is basically what I need in order to define what Lie and groupoids are. And let me go on to this.
Those two things, they are just simplicial sets for the moment, right?
Yeah, that's completely right. And then this definition of Lie and groupoid, well, I will say that is by Daskin or Getzler and Enriquez, so there are many steps going on. So a Lie and groupoid is a simplicial manifold denoted by care, where the horn projections and what are the horn projections? The horn projections are these maps PLJ, and this is KL that I can identify as maps between my simplicial L simplex and my simplicial manifold into the home of Lj of my simplicial manifolds, and the condition in order that my simplicial manifolds is a Lie groupoid is that these Hor projections are surjective submersions. For all L and J, and diffeos for all, and here I have this when L is greater than N, then I ask him to be diffeos. So the first question is, okay, yeah, this is an abstract definition. What does this have to do with the idea of a groupoid? And I agree that it is not clear a priori why this kind of objects should be called Italian groupoid. And yeah, even myself, it was really long time when I understand this something. So I'm not even clear that I understand completely what is going on. So what I want to say is just that in degree 1, this just recover. So example, in degree 1, I have that Lie 1 groupoid is just exactly the same as a usual Lie groupoid. And why is that? Is because this differ thing. So when I put it n equal to 1, that means that the only manifolds that are not determined are the k equal to 0 and the k equal to 1, because for k equal to 2, I already have a differ with this Horn filling thing. Therefore, the manifold k equal to 2 is completely determined by the manifold k equal to 0 and k equal to 1. And therefore, I can see that my triangles are completely determined just by the upper side. And the multiplication is given just by so the multiplication of these two strings, I declare that the only thing that can fill, and this is why this is called Hor filling conditions, can fill my triangle.
Okay. Yeah. A question regarding this map. There, PLJ. On the left, you have the structure of a manifold because it's one of the members of your simplicial manifold. On the right, in principle, there is an inductive construction, but in principle, you have two manifold structures a priori.
Yeah.
One is a quotient of KL. You can say that this set-theoretic map gives a partition of KL, and then the quotient is a manifold. Mm-hmm. And another one is seeing this horn, associating to each horn a collection of L minus 1 faces, mm-hmm. and seeing it as a subspace of a product of K L minus 1. And these two must agree. Is this when you write this, in which of these two constructions you think? Are they equal, and how is the easiest way to see it, etc.?
So, what I'm following here is basically, I think that Chen Chang have this inductive construction showing that this thing can be made as a manifold, and what I'm following here is the articles by Chen Chang in, I think it's 2004 and 2005. I think it's called Italian groupoids. So I think that what she is following is the quotient construction, if I'm right. So that's basically made it by induction. Once these things are diffeos, then by induction these things are manifolds. Yeah.
I think at the end of the day there are like two equivalent approaches. No? One is saying that the thing on the right is a manifold, as you are saying, with an inductive construction, and then claiming that the map is a stochastic submersion. And an alternative one is saying that the self-theoretic map gives a partition, Godeman criterion tells you when a quotient of a manifold is a manifold, and then you gain a structure on the quotient, and then you have to somehow see that the...
Yeah, probably you know better than me the construction. So I think that what we are following is the inductive process where we think this as a quotient. I'm not right. So let me just say another example of a higher object. So suppose that I have just a graded complex of vector spaces concentrated. Do I make it? No, I want to make it in this way. Concentrated up to degree n. And then this is just a graded vector space, or DG, differential graded vector space. And then you can create a simplicial manifold that where KL is just given bi of L over I. And then again, I'm not telling you the phases and the generacies, but this involves the differential. And this is basically Dolkan, an example. And this object is right now a Lie groupoid. So this is the end that is appearing here. And two comments. If I replace surjective submersion by submersions and diffeomorphism by just injective et al., then I will call it this a local Lie group. And it is called a Lie group if K0 is just a point. So those are the things. And in order to go to M-shifted symplectic things, what I need to define is the tangent complex of this object. So the tangent complex is just a complex of vector bundles over, so this is a complex of vector bundles over K0. And this thing, I just put it, the kernel of the tangent of the last Hor projection restricted to K0 for L bigger than 0. I put it TK0 for L equal to 0, and I put it here for the negative false. And here what one can say is that if I have a Lie groupoid, since the Hor projections are diffeos for L greater than N, therefore this kernel should be 0 if N is for L greater than N. Therefore the complex, the tangent complex of a Lie groupoid is concentrated in degrees 0 to N. And I need to give you the differential. And the differential of this complex is just the last phase map restricted to this kernel thing. And I'm seeing, so you see, this is K0. So K0, I can see it as a subspace of all the KL just by composing the first degeneracy map. So I see it as S0, 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 L times, and then K0 is inside KL by doing this, all these things. So let me give an example. So, so I have this complex, and the homology group, so since this have a differential, the homology groups of this complex, I will denote it in this way. So let me give an example for a Lie groupoid. G over M, the tangent complex is just A in degree 1, Tm for L equal 1, L equals 0, and 0 otherwise, because Lie groupoids are just Lie groupoids, so it's concentrated here. The differential, so let me write it maybe in this way. The differential is just rho This is 0, this is 1. And the homology groups are just, let me write this way, are just kernel of rho for I equal 1, the co-kernel of rho for I equals 0 and 0 other. So as you can see, the homologies do not form a vector boundary over K0 because these things have not constant rank. So these are just a collection of vector space over K0, and at each point you can change it the rank. Okay, so once I have this thing, I can talk about differential forms that we already know it. So this is nothing special about linear groupoids, but just about simplicial manifolds. If I have my simplicial manifold, then I have a double complex. So in one side I have the RAM, and in the other the simplicial differential. So the RAM is just increasing the degree, the RAM degree by 1. This is A. And the delta is the simplicial differential that is increasing. This 3 minus 1 to this K again, Kp. And then this is just given by the sum over all the collections of my phase maps or pullbacks of my phase maps. So inside of this thing, I have the normalized subcomplex that are just the ones. So these are normalized. That are just the ones that are annihilated by the degeneracies. And then I can define it with an M-shifted K-form. So M-shifted K-form are just the alphas. And here I have a collection from I equal 0 to M of alpha, and each of these alpha live on the normalized complex of K plus M minus I of Xi. So this is what already appeared before. So these things are living in the diagonal M plus K, and they started, as you see, in degree 0. So I have, when I is equal to 0, I have a K plus M form, and then this goes into Km, where I have a K form, and that's stop, because it's the maximum thing that I have over there. And then I say that this K form is closed if it's closed with respect to the total differential, that is delta plus minus 1p of d.
So let me just interrupt you for a second.
Yeah.
For the people that are online, if you want to ask a question, put your question in the chat, and one of us will ask the question. Sorry.
Okay, thank you very much. So I have this, the RAM complex that already appeared. Let me just, one piece missing, that is what is non-degenerate 2 form. So this was the most important contribution of Getzler when he was giving mini course on the main definition. And for that, I need to introduce this IM pairing of a two-form. So I have alpha and M-shifted two-form. And then I want to define the IM pairing. What is this? And right now you will see why I introduced it, all the things. So B and W are two vectors on the tangent complex, and B have degree I on my tangent complex of K. W have degree M minus I on the tangent complex. And right now these things are the sum of shuffles of I M minus I shuffles, and there is the sign of the shuffle, and here I have alpha M, and I use the S sigma M minus 1 into S sigma M minus I of B, and here Ts sigma M minus I minus 1 till T sigma 0 of W. So once you see the definition, it is not completely clear what is happening. So what is happening is the following. I have my B that is in the tangent complex of degree I of K. So that means that this is living in the tangent of Ki. I use the degeneracies to pull it back into Km, and once I am in Km, I use it the alpha. And here, this is in degree M minus I pull it back into Km, and then these are two vectors, two tangent vectors in Tm, and therefore I can use it the alpha M. So the non-degeneracy condition just depends on the leading term of the two form in this alpha M, and I will call it M-shifted symplectic groupoid. So let me give the definition. So M-shifted symplectic groupoid is just K is a Lie groupoid, and then the alpha is an M-shifted two form that is closed. That means d alpha equals 0. And second is the IM pairing, this lambda alpha is non-degenerate on the level of the homology groups of the homology group on the tangent. So what does it mean? So remember that these homology groups, look, I just erased them, they were here. They are not a vector bundles.
Just
Yeah.
tell you on Zoom, we don't see your line below. Maybe you need to exchange the boards.
Sure. Yeah, that's it. So the non-degenerate condition just means that these alphas, this IM pairing, these lambdas, it's defined at the level of tangent things. The fact that it is closed, so in fact I just need that delta alpha m is equal to 0, and the fact that it is closed guarantees me this condition. This condition already implies that the lambda m descends to a pairing on the level of the homology groups. And what I'm already demanding is that at each point of K0, the vector spaces at that point of H, M minus I, and HI are isomorphic.
There is a question in the chat and also an answer. So I don't know whether you should I read to you?
Yeah, sure.
Yeah, for non-necessarily non-degenerate, no closed shifted two form, doesn't this theorem respect the differential in the tangent complex?
If it's not closed, no. So
Okay.
that's the answer.
Okay.
So if it's not closed, you cannot descend to the homology groups. Therefore, it doesn't respect the differential.
It agrees with the answers that people give on the chat.
I have another question. When you define the M-shifted K-form, I mean, you don't have an element on the diagonal,
I have an element on the diagonal.
but it's truncated. It's
It's
not on every degree.
Yeah, it's
And
not
I was
every-
wondering how this relates, maybe it's a matter of terminology, with what Camille was telling us about the degree, no? Is this...
So you see, I'm calling this a K-form because in the top degree I have a K-form.
Yeah.
And in the other degrees I have things higher.
But you don't go through all the diagonal. You stop.
I just go to the K-forms.
Yeah.
And then you go higher.
Sorry, is that the definition of degree M or something like this? What is the degree of
I think it should be the same.
I think that should be indicative.
Yeah.
Okay.
You don't have anything on G2.
So let me say just a couple of remarks. So the first remark is that by the definition, if the zero homology group and the n, so suppose that I have a Lie groupoid, and then the zero homology group and the n homology group are different than zero, then the only symplectic structures that I can have are n shifted symplectic Lie groupoids. So that's the generic case, because generically you will have something that the two homology groups are different from zero. So in general, the M and the N agree. But you can have different definitions when some of the homology groups are going to zero. I also want to say that this condition here of being non-degenerate at the level of the homology groups can be rephrased as this thing, or a sharp version of this being a quasi-isomorphic between tangent and cotangent complex. So that's the same.
Mikel, another question. You are saying generically M and N are equal. When they are not equal, isn't it the case that, talking about stacks, since you did that before, you are modeling an M stack with an M groupoid with M greater than M? And it's as if taking...
Not just that case. You can have some metal things as well. But that's one of the cases.
Okay. I see. Thank you.
So the other thing that I want to talk is the symplectic Morita equivalence, and I will be really fast. So an hypercover is just a simplicial map between two Lie groupoids. And what I demand here is that this di's Fi, this thing between the matching space, should be surjective submersions. This side. And this is an hypercover and a symplectic Morita equivalent. So suppose that I have here G alpha, and then I have G dot, and then I have here K, phi, and here I have H and beta, and here is H. So I say that G alpha and H beta, two symplectic, shifted symplectic groupoids, are Morita equivalent if I have another Lie groupoid in the middle with this thing that is an M-1 shifted two form. So phi is an M-1 shifted two form, satisfying that G alpha minus H beta is equal to D of phi. So basically, I can reinterpret this as I have a Lagrangian some manifold in this derived sense of the product of these two groupoids with this change in design, as always. And G and H are hypercovers. So what I want to say is that for Lie1 groupoids, I will not show it that, but for Lie1 groupoids, there is a definition of shifted symplectic Morita equivalence by using here B Hamiltonian spaces that are a particular example of principal bibundles. And our definition and the definition that was by Pinshu, they define the same equivalence relation. So hypercovers, using hypercovers or using principal B Hamiltonian spaces is the same in the case of degree 1. And in higher degrees, I believe that should be another definition using principal, higher principal bibundles, but I don't know what those objects are, and therefore we just use it hypercovers. So let me go to the examples. I want to, well, before making the 3 examples that I promised to you, I just want to comment on another example that is of the integration of a Poisson manifold. So this should be really short. So
And if you just have a Morita equivalence and an M shifted on one leg, you can make the other leg M shifted and Morita equivalence.
so you are asking if this is M shifted.
You transport it via an arbitrary Morita equivalence to.
It is not clear yet for us, but we expect that. Yeah. But I don't know if. So if the 2 legs are symplectic, then whatever you put here, it's enough. But maybe if these legs you want to transform, maybe you should have some condition here. It's not clear, but we expect that. Okay, so let me just say, if I have a Poisson manifold.
This one.
Yeah.
One question. Is it not? If it's always possible of there are obstruction to finding a Morita equivalent representative where alpha becomes strictly non-degenerate. I mean the K form. I mean the 2 form part is strictly non-degenerate, not only in cohomology. Or are there counterexamples where this doesn't happen?
I don't know. I don't know. My answer is I don't know. So suppose that I have a Poisson manifold.
Isn't this true already in degree 1? That I can have a symplectic groupoid, a Morita equivalence, and the other leg doesn't have to be, cannot be symplectic. It cannot be a symplectic.
I think that up to some gauge transformation, probably you can do it in degree 1, maybe.
Maybe just in the audience when you have question, if you can say it louder so people online can also.
So maybe I just will say that for a Poisson manifold, let me say it in that way. So this is Poisson. So and this is Baisu. A Poisson manifold always integrate to a little groupoid. And this is basically going, so you have in the path space, you have the foliation given by path homotopies, and you pick it transversal to that foliation. And with that transversal, you can construct a little groupoid. And what we show is that this little groupoid is in fact, two-shifted symplectic. Sorry. This is one-shifted symplectic Lie2 groupoid. So here you have an example where the 2 things do not match.
Because an étale obstruction.
Exactly. And this is one-shifted symplectic Lie2 groupoid, and basically the cohomology in degree 2 of the tangent complex is 0. This is the and therefore, what we can say is that now 2 Poisson manifolds, Mi, Pi I, are Morita equivalent if and only if, or that's our definition, if the symplectic groupoids, the shifted symplectic groupoids integrating symplectic Morita equivalent. So this is something that we didn't explore yet, but I think that probably this gives a definition of Morita equivalence for non-integrable Poisson manifolds in the usual sense. And probably I hope that this definition should agree with the one proposed by Joel Villatoro, but we don't know yet. So this is work in progress. So let me go for the last example of these three examples of BG in the. I have 2 minutes. I think
That's negotiable. What about 5?
5 minutes. That's perfect. Yeah.
Good. I will take 30 seconds. This two groupoid is infinite dimensional in each level, right?
These two groupoid.
It's made of paths and homotopes.
No. This two groupoid is finite dimensional in the first two, and I think that is infinite dimensional in the third one.
Ah, yes?
Yeah.
Okay.
So here I put it M. Here I put it M. Here I
Transversal
put
is finite dimension.
the UI.
The transversal, take the transversal.
I will take
Yeah, you pick it transversals, and here you put it this UI times some monodromy of this foliation. Yeah. So this is that's the main issue. Okay, so let me go to the last thing.
But so then this is equivalent to the infinite dimensional one, the natural. Yes. Okay.
So let me say that I have a quadratic Lie algebra, and then I have just an easy integration of a Lie algebra, that is the Lie group that integrate, and therefore on the nerve of my Lie group, I can put a two-shifted symplectic two form. So this is two-shifted symplectic. And what I'm putting? Well, in the level 2, I put it just using the second phase map. I just pull back the Maurer-Cartan's forms to the second level by using my phase maps. So this is a 2 form on G times G. And then I'm using the pairing on the Lie algebra to construct the two Lie algebras. And then on the level 1, I put it this 3 form, that is the Cartan 3 form. Theta left, theta left. And this leaf, just a 3 form on G. And this is a two-shifted symplectic groupoid. And this basically goes back to Brzezinski and Weinstein, this definition. And which are the properties of this thing? Well, the first property is that clearly mg differentiate to little g. The second property is that if I apply the Van Est map that goes from the RAM, so the Van Est map defined by Marius Kreinik and Camillo, goes from the RAM, from this double complex to the RAM basically of the G1, of the little g. So the Van Est map of this gives me minus the pi ring. And therefore, the two things differentiate to, so the symplectic structure goes to the symplectic structure here. And the last property is that the total cohomology class of this is the first von Triagen class of the classifying sphere. So this thing represents a 4 class here on Vichy, that is the first von Triagen class. The second model, it's an infinite dimensional model, and goes back to Siegel, maybe Baez, Enriquez, and also Eckhart, Menreken, and Woodward. And what I put is this infinite dimensional model that on level 2 I have the loop group of my G, on level 1 I have path, and here I have a point. And the 2 form, I have just a 2 form on the loop group, that is dw. This is the integral over S1 of the tau t, bt, b prime, tau l, tau t, wt. And this is just the usual 2 form on the loop group of G that is again induced by the pairing. So this is some kind of transgression. And the important thing here is that this space appears as a symplectic reduction using the Chern-Simons sigma model. And the symplectic form appearing from this symplectic reduction is this one. This was computed by Van Reken and Woodward. Therefore, I think that this kind of picture should be generalizable to general current algebroids. Let me give the third example, and I will finish. And the third example is using main triples. So if you have a main triple, then I have my H that is endowed by this main triple structure. Then I have a double symplectic groupoid that was constructed by Weinstein and Liu. And it happens that Russian Mehta and Chantan make it a bar construction to create a Li2 groupoid that in general is local. And it happens that, for example, if these Poisson groupoids are complete, then it's a Li2 groupoid, but in general it's just a local Li2 groupoid. H minus H plus, and then I put here H plus times gamma bar times H minus, and then the two form omega H is just the projection, so it just lives in this factor, in the middle factor, and this is just source, the target of H, of the pullback of the Maurer-Cartan of H plus, the source of the vertical of H minus, and then there are the same thing here, but just changing the things, H minus and source H and theta right of H plus. So what you see is that the three things are really different, and what we prove it is that, well, there is an hypercover here going to G cross G and going here, that this is basically the end point of this path, and here you need to combine things. And there is as well some map that is here just, multiplication of these two things inside the G, because G is like the double that integrates, so the dream field double that integrates G, while this just integrates half, and here you can create another group, and then you pull back the things, and the two forms are not equivalent, but they are equivalent up to some term that is really explicit. But I didn't have time to show up, but the article is in archive and you can look it up. So thank you very much.
All right, so we have a little bit of time for questions. There are many questions on the chart. Maybe let me start with one of the questions on the chart, because they were already writing for the last 15 minutes to us. Let me see, where should I go? Yeah, there are many questions and answers. Maybe I skip this non-degeneracy or this closedness story. Maybe you should kind of look at the chart and answer them by email. So then there was a comment of Pavel Safonov. I thought the question is basically whether functions of the shifted symplectic stacks presented via shifted symplectic n groupoids carry Poisson bracket. In particular, the Lee-tree algebra that Camille wrote down is a truncation of functions of the cotangent bundle. Is there an explicit bracket on the whole groupoid homology of the cotangent groupoid, and not just its truncation?
Yeah, I think that's a good question. I don't have an answer. A priori, you see these forms are degenerate, so in the usual sense, so are just non-degenerate up to some term, some homotopy. Therefore, I'm not sure about which kind of a structure can you associate it in general, even for the functions on the whole complex of the Lie groupoid. So which kind of bracket or which kind of operation you can associate. But I think that something should exist along those lines. But which kind of a structure, I don't know. So our point here, and this is the main tool of this VG, is basically provide concrete geometric models where you can do geometry instead of working with the stack.
Okay, maybe some questions in the audience here on site.
Yeah, when you define these forms, no, M shifted. In the case at least when M equals 1, you can realize this form as a VV map, a map of vector bundles from the cotangent to the tangent, or in this case, yeah, from the cotangent to the tangent. And I was wondering if you have worked out a way to see one of these structures in a similar way as a...
So you can try to do it. So the first thing to do is, well, this, as I say, this can be shown as some kind of sharp map between the tangent complex. So instead of working with the tangent complex, the first question is what is the BB cotangent of a Lie groupoid? And I think that I have an answer for that. Once you have that, the next step is to show in which sense the M form, that is a 2 form, can be defined if you a map between the BB tangent and BB cotangent. And that's the next thing that we are doing. So we are working on that direction.
The first example was with the current algebra given by quadratic Lie algebra. And there's mild generalization where you look at the action current algebroid. If you have an
action on a manifold.
X on a manifold with coisotropic stabilizers, do you know how to...
That's clearly the next example. We don't know yet. The example that I know, one of these 3 integrations is when I have a Lie algebroid, and then I look into this even higher current algebroids for any k. So for k equal to 1, I have a current algebroid. And then I know by using these cotangent things, I know how to integrate this in one example, in this example.
All right, maybe it's a good point to close the morning session. So there is still a discussion going on the chat, so there is some kind of a little bit of a parallel life there. Sorry, people kind of perhaps couldn't bring you more adequately into the discussion during the talk. So thanks a lot again.